Stan. So our paper is titled An Automated Waste Segregation System using trained optical and material sensors with user communication capabilities. So in my presentation, I will give a short introduction and show our method, testing, and our conclusion. So our introduction, of course, populations will increase and increase, and with this increase, will increase the amount of solid waste generated. So here in the Philippines, around 165% in amount of solid waste generated. So because of this, segregation at source, well, by the Philippine government, is one of the first steps in solid waste treatment. And this will help improve the volume of waste that is recycled and treated and not going into our environment. So we proposed a solution. Tried to develop a system using a computer vision model with the help of some material sensors, in this case, an inductive sensor, to help classify and segregate the wastes at source. So here is what we designed, our prototype. We only had around 4 months to design everything and create this. So it's around 0.6 by 0.6 by 1.3 meters. That's the height. So the modules included in this, what you can find in this system, in this trash bin, or if you can say that, are the infrared sensors. Infrared sensor is on top, where when you put the waste, it detects if waste has been put inside the trash bin. RGB LEDs, there are 4 of them because there are 4 compartments of 4 types of classifications of waste that we have used. These are used for visual aid, for users if they can see if it's full or not. Servo motors are used to help segregate the trash as they drop down into different compartments. The webcam is one of the most important parts of the system because this one takes pictures that we use to train our model, and we use also to help classify the waste. This is one of the most important parts. The ultrasonic sensor, which measures the waste level in the receptacle. The Raspberry Pi 4, which was used as our controller, the thing that bin. And I have not put it here, an inductive sensor. This also aids us in measuring whether metallic objects are input into the system, which I will touch on later. So we also developed a small web application, but this is just hosted locally. We did not have time to deploy it online. A web application, this was developed as a user interface. So people will be able to see the data we gathered, types of trash, how much trash, levels of waste inside the receptacle, etc. So we also use this is one of our most important, as a way for users to help improve the model. What we say about this is users will be able to see the images that the trash bin has taken, the webcam has taken, and the classifications that it was done by the system. So we have a model that classifies what type of trash it is, and we users, since we know what trash it is, we will be able to help verify whether it is correct or not. This will be help used in continuously improving our system. So in order to create this model, what's very important when we train computer vision models, convolutional neural networks, is that we need data. And so we have for this, it's actually really small data set. This is just 2,286 images we have collected. And as you can see in my slide, these are the 4 examples, because we only have 4 categories at this time: metal, paper, plastic, and other trash. These are for, in order to recycle them. So these are the 4, an example of each photo that we have taken. And not only the photos that we have personally taken for this project and our trash bin has taken, but we also used another data set of trash collected by Mindy Yang and Gary Thung. It was a data set from Stanford University, if I'm not mistaken. So the model, this is a convolutional neural network. It's just like in the brain, neurons. These neurons, as you can say, help classify by transforming the pixels into data, numbers. And these numbers, as you can see, it says images, feature extraction, and classifier. So this is like the steps it goes through. So the images go through the model, which is a feature extractor. It means it gets the shape, the color, the different sizes, etc. of the trash, and it classifies them. We teach it to classify into 4 different types. And there's, because we had a lack of time, we had a pre-trained model that was trained to recognize around 10,000 different objects, which was not what we wanted. We want a specific one for the 4. So we just tested it out first to see which was more compatible for our waste reason. So we decided to choose this one called VGG16. So here we tested it out on the images, and as you can see, it has a high accuracy, meaning it was correctly classified the waste 92% of the time. This was without any data augmentation. We did not change anything about the data. It was just initial testing with a loss of 0.6. Lower loss is very important. And as you can see, one of them is around 100%, but it has a very high loss, so we did not decide to choose it. So in our testing, because it is still, this pre-trained model is just for very wide different types of classes. We need it specifically just to recognize types of trash. So we had to train our model. So in our parameters, it says train validation split of 80-20. We mean by this is 80% of the images are used to train. We give our model these pictures that we have, and we teach them, okay, this is a metal can, this is a paper. How we do it is that it goes through the photos, it extracts the types of features, the size, the color, etc. And it creates connections like, okay, if it's this color, or if it's this shine, if it's this shape, it usually is this type. So it gives out predictions. It's the image size, of course, image size. Batch size 12, meaning we give the photos by 12, and epochs 30. Epochs, when I say that, it means we go through all the photos 30 times. So we went through all the photos, around 2,286 photos 30 times. The validation means we use these 20% of the photos just for testing. We did not use it to train, we tested it out. So as you can see, after 30 times, our accuracy is around 77.6% for training and the loss of 0.6, and our validation accuracy, meaning the test photos, are 83% and a loss of 0.39. So here is a graph. During training, as you can, there's on the y-axis the accuracy here on the left, and on the x-axis is the epochs, meaning after how many iterations of the photos. So it increases, slowly increases, and here the loss, which is what we want, slowly decreases. Once we trained our system, we tested the model just for photos. We have to test it physically. We built our own prototype. We threw trash in it. And as you can see, here is our results for the testing. Accuracy, this is 100% metals. Paper 80%, plastic 92%, other trash 84%. So as you can see, there's metal is 100%. This is because we had a material sensor of 100%. Material sensor, sorry, that detects metals too. So this helps us to make the system more accurate, especially when it comes to metals. So and on our right, we also timed the speed just to check what if the types of trash are aid in the speed. As you can see, it all looks similar. So that goes to show that the classifications don't really matter when it comes to speed of segregating the trash. So what we can conclude for this is the automated waste segregation system, it is able to segregate waste at source, and it can continuously be improved, which is the most important part, we believe. This train model, the classifier, can be used in other systems, not only just our own. The accuracy and loss, which is very important, it's still kind of low, 80%, 83%. This can easily be improved as we collect more and more data to make it more and more accurate. And we have more time to train our model. And the speed of the classification, which is also somewhat important, um, is not reliant on the classification, but is just optimization of code. So that's it. Thank you for listening. Um,
Thank you very much, Mr.